I'm another one of the PhD here on Locusys, and Andrea already explained about the structure of Locusys. I just wanted to say that I'm in project area A, concerned with electronic systems, and also A1, the first area. And the focus for me during my PhD is going to be to develop an optimization platform to design these assistive devices with this specific point, which is the theme of the whole project, to involve users and their perspectives in the design process with the aim of making it more usable. So this is an overview of the optimization platform. I'm not going to go into details of this, but just to show that you have some drive concepts for the actuation. You have some movement scenarios, which could be a combination of scenarios, and you want to optimize the cost function. I'm going to talk specifically about the cost function because it's the most challenging part of it, since I'm not aiming to just include objective criteria. I'm also going to try to add subjective criteria coming from the users, somehow objectify it, and add to the cost function, then include them in the design process. It looks difficult, it is difficult, but probably the next study would be a possible way to go about this very difficult problem. We decided to look into brain-computer interface, specifically passive brain-computer interface in the field of assistive wearable devices. And this first proof of concept study, we tried there to simplify the problem as much as possible. So what we did was we are using these assistive devices in very heavy intensive movements, but then there's the problem of movement artifacts and the EEG signals. So let's do it while sitting down. How do we do that? Well, there are specific muscles you can, or joints you can activate while sitting down. The knee joint is one of them. That's what we did. A simple 1 degree of freedom knee exoskeleton that has one variable parameter, which is this mnemonic artificial muscle, and it can have 6 pressures, so 6 stiffness for the device. And we ask subjects to do this flexion extension of the knee joint while sitting down, watching a reference trajectory. We ask them to follow this reference trajectory as much as possible. And in each trial, we had one of these 6 values for the PAM, which created more difficult or easier movements for each subject. And we asked them the following question to give us a score from 1 to 5, 1 being very easy, 5 being very difficult. And the question was, how easy or difficult was it in this specific condition to do the task? And the task is to, of course, follow this reference trajectory. We had 6 conditions. We repeated each one of them 20 times. Why 20 times? Why not more? Because this creates 120 trials. If they want to do each movement for at least 20 seconds, then it's approaching 2 hours. With the preparation, it's 3 hours. We couldn't do much more than that. And this is a video of the experiment. First, when they come in, we do the preparation, which is setting up the EEG device, the exoskeleton, getting used to the system. This takes anywhere between 30 to 45 minutes. My record was 15 minutes doing it alone for the last participant. We did 14 so far. And then we do reference determination. So as I mentioned, it has one actuator, simple pneumatic artificial muscle. We detached it. We have them do the movement with their preferred range and frequency. And based on that, we determine the reference trajectory for each participant. Then we do the trials by adding the actuator. So as I mentioned, each condition was repeated 20 times. After each 10 trials, they get 2 minutes of rest, and in the middle, so after 60 trials, they get 15 minutes of rest. And what they do is, as you see, following this reference trajectory, then they, whenever, after at least 15 seconds of movement, whenever they feel like they can give a score to this condition, important, we don't ask him to compare it with other conditions, we just ask him how difficult it is now to do this, given the current state of the device. She stops, she gives me a score between 1 and 5, and then we move to the next one. The goal is basically whether we can interpret their scores without asking them, but just looking at their brain signals. Quickly going through the data analysis. One way is to search for a feature there that correlates these two variables that we have. Another one is use machine learning, which is a little bit easier given the size of the data. So, quickly going through this, we have the raw EEG data of 32 channels for each participant, labeled, so each trial has a label, which is the score they gave, 1 to 5. Then we run through these paradigms. These paradigms, you can think of them as filters, spatial, temporal, and spectral filters, various methods. Then we extract features, train a classifier, and then through cross-validation we determine the misclassification rate. Since I don't have much more time, then I will show you the initial results and the current state of the analysis. So here are the results for one participant, participant 8. This is where we trained the classifier, and then we applied it to participant 10. And this is the misclassification rate, so the amount of time that the classifier misclassified the class. And the classes are easy and difficult, so we narrowed it down to 2 classes. As you see, this looks terrible, but does it really? So these are the generic paradigms with generic settings. Each one of them has quite a lot of variables. We can do variable searches, we can use other methods, more complicated methods, and my point here is we can only go up from here. And even now, you see dual augmented Lagrangian method, when trained on participant 8, has around 80% accuracy in classifying whether they would say this condition is easy or difficult. So that's the whole thing. Looking forward to your questions.
Yep. Is following the trajectory would representative of walking? Because I'm not sure, but I think that trajectory, following trajectory is not very popular.
Yeah, so we didn't, it's not directly related to the final application. We just wanted to design a simple scenario where the goal for us here was for subjects not to move their heads. Because if they move their heads, there's movement artifacts, then we have to go through the whole process of removing those movement artifacts. But then we tried to see if we can interpret their evaluation of the difficulty of the task by just looking at their brain signals, not asking. So the task is simple. Follow this reference trajectory. You can think of it as a training. So you want to train your flexor, your knee flexor extensor muscles, and you increase the level of difficulty of this movement. We wanted to see if we can interpret their evaluation of how difficult it is by just looking at the brain signals.
What's the use case of this though? It seems
Okay.
like a very complicated way of asking somebody how difficult something is.
Well, the use case, the final use case is if we could interpret their evaluation of the difficulty or whether, so the difficulty would be thought of as whether the device is helping me or is it resisting. So in this case, it's a resistance act. So we want the device to resist your movement. So during the training, you're pushing more, for example. If we can interpret their evaluation of the current state of the device by just looking at the brain signals, then we don't need to ask them. And if we can apply the same principle to an exoskeleton while walking, then we could change. So you think of it as a preference. So you ask for the preference by changing a control signal, control parameter of the device, right? You can either ask them directly what is your preference by changing this parameter, which one of them do you prefer, or you can interpret their preference by just looking at the brain signal. So that's the ultimate goal.
All right, sorry, we didn't solve it.